Welcome to Ask and Learn.
In this problem, we have a cylinder that is initially filled with air at a specified state. The air is electrically heated at constant pressure, and some heat is lost in the process. We wish to calculate the amount of electrical energy that is supplied in the process. Now we assume that the cylinder is stationary, and thus the kinetic and potential energy changes are zero. We assume also that the air is an ideal gas and has variable specific heats. The thermal energy stored in the cylinder itself and the resistance-wise is negligible, and the compression or expansion process is quasi-equilibrium. Now, the first thing we do is find the initial and final enthalpies of A. And the initial enthalpy H1 from our tables is the enthalpy at the initial temperature, which is 298 Kelvin. And this is 298.18 kilojoules per kg. The final enthalpy of the system, H2, is equal to the enthalpy at the temperature T2, which is 350 Kelvin. And again, from our tables, this is 350.49 kilojoules per kg. So now if we take the constants of the cylinder as a system, and the system is closed since no mass enters or leaves, we can write the energy balance for this closed system as the energy in minus the energy out is equal to the change in energy of the system. Now the energy into the system is electrical energy due to the resistance heater. So we have work done by the resistor, so that's the work done by the electrical energy. And we have some heat which is lost, so minus Q out of the system minus the boundary work W, which is also out of the system. And this is responsible for a change in internal energy delta U. So we can rewrite this equation by taking the boundary work across, and this becomes the work done by the electrical energy, which we wish to find, is equal to the mass of the air in the cylinder into the change in enthalpy H2 minus H1 plus the heat that leaves the system, Q out. And this is because, remember, delta U plus the boundary work is equal to the enthalpy change delta H. So we use this relation in our energy balance equation. So what we need to do here is find this work done by the resistance heater. And we can do this as follows. So the work done by the resistance heater, the electrical work done, is equal to the mass of air, which is 15 kg, times the change in enthalpy, which is 350.49 minus 298.18, and that's kilojoule per kg. So we found these from our table, plus the heat that leaves the system, which is 60 kilojoules. So in one go, we actually can find this work done by the resistance heater, and this is 845 kilojoules. So we want this work in kilowatt hours, so we'll multiply this kilojoule by conversion. 1 kilowatt hour is equivalent to 3,600 kilojoules. And so we get the amount of electrical energy that is supplied, or the work done by the heater, to be 0.235 kilowatt hours.